Let us start with a small exercise today. Suppose I have this state. Okay, you can think of it, this state, as coming from this experiment where you have a set of n elements from the set S0 and S1, and then when you apply the function value to it, so let's say you have header mode, you have state 0, you apply the oracle. So S0 is the set of values for which the function value is 0. Okay, and S1 is the set of values for which the function value is 1. If this is the case, header mode to the, this will convert, header mode will convert it into equal superposition of x. Then for every S0, I will get 0, 0 XOR fx. For every S1, I will get f1. Okay, so this is the state which you will get here. Okay, my question to you is, I know that on most of the inputs, my function value is 0. On 2/3 of the fraction, my function value is 0. On 1/3 of the values, my function value is 1. Now, if I measure the register, let's say both registers, what is the probability that I get 0? So you don't have to worry about how do I create this state. I create this state, I measure. What is the probability that I get 0? Okay, one answer is 2/3. Anyone else? How many people are convinced that the value is 2/3? 1, 2, 3, 4, 5, 6. Okay. Why is it 2/3? So, and every S0 will appear with probability, every element of S0 will get the probability of 1/n. So 1/n multiplied by 2/3 times n. So you get the probability 2/3. Right? Why didn't you solve question 3 with this? In quiz 2, that was exactly the problem, right? This is the simple thing. I told you that for on 2/3 of the indices, the value is 1. On 1/3, the value is 0. You create an equal superposition, apply the function, you will get your value in the second register. I thought this was a... but okay, let's not worry about what happened in the quiz. Let's focus on today. Is this clear? The probability by which you will measure 0 is 2/3. It is not square root 2/3. You are not going to add the amplitudes on 0 and then square it. That will violate all laws of probability. They will not sum up to 1. Right? So the in general, okay, this is my state, correct? What is the probability that I measure 1 in the second register? This amplitude square plus this amplitude square. We have done this before, right? So in this case, this will be 3/4. Is there any doubt on this? We are okay with this, right? It's quite clear. This is not no. It is half square plus half square plus half square. Right? Makes sense? This will not add up to 1. This is completely wrong. We are fine? If there are questions, I would be happy to settle this later. But this is a basic example. In the first resistor, you can have 4 states. Out of, let's say in the equals observation, 3 of them give you 1, 1 of them gives you 0. What is the probability that you measure 0? 1 by 4. What is the probability that you measure 1? 3 by 4. In general, if it was alpha 0, alpha 1, alpha 2, alpha 3, the probability of measuring 1 would be mod alpha 1 square plus mod alpha 2 square plus mod alpha 3 square. Right? These measurements we have done before. Okay, let's wipe the history clean. We start afresh. Okay, we are in for exciting times. We are going to learn Grover search. Okay, ready? Welcome to another lecture on quantum computing. We are going to start fresh. We are going to learn Grover search, and not just that, many modifications to it, and actually see why it is optimal. So this is something which will be new for you. How to prove that whatever you do, you can't do better than a certain amount. Right? This kind of results are very hard to prove. Human brain is brilliant, and you are putting limits on human brain. Whatever algorithm, not just classical, whatever quantum algorithm you come up with, you can't do better than this. Okay? We will try to prove such results also. But anyway, let's start with simple things first, Grover search. And for Grover search, we need an essential idea. The essential idea is listed here. I haven't given the heading to this picture for a reason, because you will tell me what is this about. Yes, Eliezer Woodman.
So this is a modification to that, so that we get the maximum probability of the bomb not blowing up, but we're still finding out whether it is a dud or a real bomb.
Good. So this is the modified Eliezer Woodman, where the probability for explosion is going to be really small, and we are going to able to still say whether the bomb was real or dud. Remember this? Okay. So good, very good point. This is not Hadamard, this has to be converted to the rotation. Hadamard is rotation by 45 degree, but we wanted to slowly rotate it to 1 for Eliezer Woodman, right? So this was the case. Again, I just want to take a lesson out of it. You can again read about it. I have explained it more clearly in the notes, in the fresh notes. But the point remains, what happens is that if it is a bomb, every time the probability that it explodes is sine square theta. Okay, if I do this k times, the probability of exploding is k sine square theta. If the bomb doesn't explode, my state every time I measure gets changed to 0 again. So I measure 0 with the remaining probability. Okay, so once more, here the probability that bomb explodes, or I measure 1 here, was sine square theta. This experiment I am doing it k times, so the probability that it explodes is at most k sine square theta. In the remaining probability, this state will go to 0. As soon as I measure and it doesn't explode, this gets set to 0 again. So I measure 0 with this probability. Okay. What happens here? If it's a dud, then I am not applying the measurement, I am not applying C naught. So this is C identity, where you can just cancel. C identity means I am not doing anything. I am rotating by r theta. So my state becomes cos k theta 0 plus sin k theta 1. So the probability that I measure 1 is sin square k theta. I start here, this is cos 0 0 plus sin 0 1. After one rotation it is cos theta 0 plus sin theta 1. After k rotations it is cos k theta 0 sin k theta 1. A state which is cos k theta 0. So the state here is what is the probability that I measure sin k theta? 1 sin square k theta, which we will approximate it by k square sin square theta. But the remaining probability, I will measure 1. And the reason why this was a success was because this goes to 1 much faster than this. Remember, right? This is going as k sine square theta. This is going as k square sine square theta, right? So this is going faster to 1. So when this reaches 1, this quantity will be still very close to 0. Right? So what have we shown? If the bomb, if it is dud, we will measure 1. If it is real, then it will explode with a very, very small probability. This is what we wanted to show. And the reason why we are learning this again is because there is an important lesson here. How did k sine square theta came? We added probability k time. Right? So this was our probability amplification. Bomb exploding probability keeps increasing every time I apply this circuit. Right? First sine square theta, then 2 sine square theta, then 3 sine square theta. So here I am adding probability. What happens here? Here the probability doesn't get up, but the amplitude adds up. Sine theta, 2 sine theta, 3 sine theta approximately, 4 sine theta. So here I am amplifying amplitude, which gives me probability k square sine square theta. This approaches to 1 much faster than this. So the lesson is amplifying amplitude is much faster than amplifying probability. Okay, so here we were measuring in every step and giving probability that the probability of success or bomb exploding was very, very small. Instead, if we stop the measurement, we keep adding up the amplitude, we get to 1 very, very quickly. Right? So this idea is clear because this is the essential idea behind what we are going to do right now. Questions? So this is what you need to remember. Rest everything is fine. You can verify this again from the notes. You can do the calculations yourself. But this lesson is very, very important. Learning this lesson, now we will go to our problem and see the famous Grover search algorithm for it. What is unstructured search? Does anyone want to take a guess? What is search? What is English word search?
We are trying to search from maybe a data structure which is not very structured and it's very bit randomized maybe.
Okay.
You can't really classically figure out a way. This is how we are supposed to go around it, and these are the paths connecting to the different data maybe.
Okay. Okay. So yes, you are right. Not completely, because you have a commitment problem. You are not committing yourself. There is no structure at all, not a bit of structure. It is unstructured search, right? So it is not like there is not much structure or there is less structure or something. There is no structure at all, right? So there is no data structure. It's basically a list of n elements. Oh, if I say that it is alphabetically sorted or something, then it is structure. But if I tell you that I have n names, first name is something, second name is something, then there is no structure. These are just n, this is a set. But whatever you want to search, that structure, whatever is there, is not going to help you there. So there is no structure. Yes. An unordered, whatever you want to call it, but no, there is no structure present which can help you search in that. So that other way to say it is that if you want to search classically, yes, Worst case, you might have to look at all n elements. Okay, very, very simple problem, probably the first problem you saw in your introduction to programming course. Obviously, if it was sorted, then we could do it in binary search. How much time? Right? So the setting is clear, we have no structure at all, it requires a lot of time. But this is a situation which is there so many times. Right? CS632 gets over, I publish a list of students who have failed, you want to search for. So, okay, students who have gotten an A, you want to search for your name, right? And because I'm sadistic, I will not sort it with roll number or with alphabetical name. So then you have to look at all of the students' name and find out whether you have gotten an A or not, right? But you want to find a website, you want to, like, search is present everywhere, right? So even if I can say that instead of looking at n elements, I can search in n by 2 elements, this is great. The speed up is not great, but this problem is so much there everywhere that any speed up is of importance. Okay, so what we are going to see is now a speed up Any guesses what this is? You should be able to tell me. No. What is this?
Worst case scenario time.
For what kind of algorithm?
For deterministic.
This is deterministic.
Oh, that's randomized, probabilistic.
Probabilistic, right? We have always known, classically we always compare with randomized. We are taking worst case cost, expected cost. Sorry, worst case cost. So even worst case cost is ON for randomized algorithm, right? So the cost will be expected over randomization, right? Sounds good?
How's the difference? Like you mentioned n and O of n wouldn't that be the same?
N is also O of n, but O of n need not be n.
Right,
Okay. So for example,
can be better than deterministic,
so-
but it may be equivalent.
so randomized would be, if you allow error of 1 by 3, this would be 2 by 3n,
Okay.
right? And what is the randomized algorithm? Pick the first 2/3. You don't know what is.
Any random.
Pick a random one, pick a random index and check. Is your name there? Is Rudraksh there? Right? If it is there, yes. If not, since there are 2 by 3 places where Rudraksh could be there, my probability of success would be 2 by 3. Right? So this is the idea this was the simple randomized algorithm. Correct? Okay, great. What you can actually show is that this is the best possible strategy in randomized. There can be a lot of randomized algorithms in searching in an unstructured list. The basic algorithm is pick a random element and check whether it is my element or not. Correct? But the one I am searching for. And that will succeed if I pick order n many elements. Right? What I am telling you is you can't do better. This naive algorithm is the best you can do because there is no structure in the list. So the only thing you can do is pick a random element and check whether it is marked or not. Sounds good? Questions? You seem confused. Okay? So the classical algorithm, you have a list, you have x1, x2, xn, right? Some of the elements are special. Okay, so let's say 2 elements are special. If I pick a random element, what is the probability that I get that special element? 2 by n. Correct? Now let's take this simple case when just one element is special, or how we say it, one element is marked, we want to search for the marked or the special element. Okay? If I pick a random index, what is the probability that it is going to be marked? How many do I need to pick to make sure that my probability of success is 2 by 3? 2 by 3n. So, if I pick 2 by 3n indices, this xi lies in this is going to be success probability 2 by 3. So, this is going to be my randomized algorithm, right? Whose query complexity is 2 by 3n. I have to look at 2 by 3n elements. What I am saying is you can't do better than this. Whatever you do. Randomized, this is the best you can do because essentially there is no more structure. Sounds good? Okay. Questions? Right? So what is the setting? Now, I have an oracle. Okay? Again, somebody has to tell me whether the element is special or not. Okay, classically I was just saying I will find out whether it is special or not. Let's say we have an oracle which tells me whether the element is special or not. Okay, what will it do? It will take an index I, it will check, it will give me the xi, whether ith element is special or not, or marked or not. Correct? So this is the oracle for my list, let's say. Now, given this oracle, I want to find out a marked element as quickly as possible. Deterministically, I have to call this oracle n times. Randomized, I have to call it theta n times. We want to see an algorithm where do it using a quantum circuit. Okay, so the problem should be clear. The problem is this: we have a list. How is that list given to us, or how is it mentioned that the elements are special or not? I can say, tell me whether the ith element is special, and this will tell me, the value of xi will tell me whether ith element is special or not. We have seen this so many times, Deutsch-Jotza, function value, whatever. Now, given a list in L elements, how many times do I call the oracle and find a special element? This is what I want to do. And it is clear that deterministically, I have to check all i's, and randomized, I have to check theta n i's. Okay? Formal proof can be given, and if time permits, I will cover it at the end of the course. This lower bound of theta. Okay? But let's see a quantum algorithm for it. Problem clear? Yes? Questions? So what should be clear to you now is the problem and its importance. We will solve it very soon with the lesson learned. But the problem is clear, right? And importance, obviously searching is there everywhere, right? We want to search for name, roll number, past people, websites. This is, Google made a lot of bucks by solving search of things, right? So search is clearly very, very important, right? So this is a basic search when there is no structure. Okay. And the fun part is that the quantum circuit or the quantum algorithm is essentially a modification of the, sorry, that's a good guess, but I'm going to say randomized algorithm. It's the quantum version of the dumb randomized algorithm. Okay, so let's just first see how this randomized algorithm worked. Okay, what was the randomized algorithm? I had n elements. I pick first element. So let's say I'm searching for Satvik's name. First element, is the name Satvik? Yes, great, I have found it. No, I pick another index. Then I pick another index. Keep going. Correct? What I can tell you is that since we do not worry about what constant is there with the n, we can even assume that, I pick an index I, check whether it is Satvik or not. After that, I will throw that element back again in the list. Okay, I will not worry about whether I have already checked that element. I can once again get that element back. The probability is going to be small still. After this many repetitions, I will find out that and this is not hard, right? What is the probability of success? I have just one marked element, right? So my probability of success is 1 by n. If I repeat it k times, what is my probability of success? Or probability of failure. This is my probability of failure. After k iterations, I am a failure if I haven't found Satvik in any of the k iterations. So 1 minus 1 by n whole to the power k. Correct? This is very big, close to 1. When does it become 1 by e? K becomes order n. This basic math. Right? When this, so correct? So this is what I am using here. So once it has gotten to 1 by e, you can make it as small a constant as you like, failure probability, by just multiplying by it by 2, 3, 4 or some constant. Correct? So now our trivial algorithm is the dumbest possible version. We are even doing repetitions now. So out of the n element, I pick an element, is the name I'm looking for, is the name Rajat. The name is not Rajat. I will throw it back in the list. Once again, I will pick it from the n elements. Okay, and what I know is that I will succeed after O of n picks. Clear? I'm really emphasizing this algorithm because we are going to modify this algorithm.
Is this converges to 1 by e? So, failure probability is
When n is large, if I put n iterations, this will become 1 by e. But if I want failure probability, let's say 0.1, I can convert 1 by e to 0.1 by repeating it k times, right? Constant many times. So constant times n will be equal, will be fine. Okay? So you can do this calculations on your own. If you get stuck, so as we increase the iterations, my failure probability will stop dropping from 1, it will get closer and closer to 1 by e. Correct? What this is saying is that if k is around n, it is already 1 by e. And if I want to reduce it further, I repeat this entire experiment some constant many times. Okay, then this will go from 1 by e to 1 by e square, 1 by e cube. It can be brought down. But the point is the number of times I have to repeat is constant times n. Okay, so if n is big enough, then this is 1 by e plus 0.1, but bounded by 1 by e plus, that's good enough for me. Right? Okay. Cool. Okay, so the dumb algorithm is pick an element, check if it works. Doesn't work, keep doing it again. Right? We will keep this lesson because obviously this is the most important thing. So, stage 0, I am here, I toss a coin which has n possible values. Correct? I can check index 1, I can check index 3, I can check index n. Okay? Which one do you want to be the marked element? Favorite number? Huh? Oh my god, you physicists are different, man. Even numbers are nicer. No? Right? Obviously, even numbers are much better than odd numbers, no? Okay, 3, but we'll go with Sayesh. 3, right? 3 is marked. So what happens now? This I get with probability 1 by n. This I get with probability. If I reach here, my experiment is over. Right? What happens here? Reset, repeat. I once again toss a coin which has n possible values. Right? I'm once again picking an element from the list, which could be any of the n elements. Correct? Right? Once again, this is what is happening, right? Correct? So, what is the probability that I get 3? I can get it in one step, or 1 by n square, no, 1, you mean this, right? Okay, 1, 2, in n minus 1 cases, I can also get 3 in stage 2, correct? Right? So this is my probability that I get 3, correct? Probability of anything else, 1 minus this divided by n minus 1 by symmetry. But you can also say I can get it in each of these with 1 by n square probability, right? So this is stage 2. This is the probability of getting any other element, any particular element. So probability of 1 or probability of 2 or probability of n, unmarked element after 2 stages. So here, this is also after second stage. So this is calculating probability after second stage, right? So this is probability of getting a particular unmarked element. No, not n minus 1 square. I will be either here, okay, what about probability of 1? I will get 1 if I come from here, or here, or here, right? What is the probability that I get from 1 from here? 1 by n square. What is the probability that I get 1 from here? 1 by n square. There are n minus 1 of this, right? And you can check all this by the law of probability. It should sum up to 1. Okay, so you are right that the total probability of unmarked elements is n minus 1 square by n square. But the probability of just one particular unmarked element is this. Okay? What I'm trying to say is that this is approximately 2 by n. This is slightly smaller than 1 by n. N minus 1 by n square is almost 1 by n. This is almost 1 by n. So this is 2 by n. I can plot these probabilities as histogram. So after stage 1, everything will have a probability of getting 1 by n. Correct? This is trivial. What happens after stage 2? So this was my line 1 by n. Everything is slightly smaller except Suyash's favorite element has gone to 2 by n. Approximately 2 by n. Right? Is that okay? No. If this was n instead of n minus 1, it would be 2 by n. This is your exact probability. 1 by n plus it is slightly smaller and smaller than 1. Right? So I will say approximately 2 by n. Okay? You will do these calculations in the assignment. You will see what is your guess after 3 steps? Again, all of these, the 1 by n of that will go here. In this, I will once again toss a coin. Correct? 1 by n of it will hit 3. So again, all of these, approximately 1 by n's, will contribute 1 by n square to this. So again, this will get raised by around 1 by n. Increased by 1 by n, total it will become 3 by n. These will become slightly smaller. Right? This is what your randomized algorithm is doing, and after around n steps, this probability will become constant, as expected. Right? So I have just explained the classical dumb algorithm using lot of pictures and histograms. We have done a lot of analysis to see that small thing that after around n steps, this bar will reach constant. Right? The probability of success will become constant. I have to repeat this after n repetitions. This will become really, really small. This will become, sorry. Right? I'm not doing exact calculations, but this is what it is happening, right? Okay? Correct? So what happens at every stage? If I look at this stage, all of these take some probability and add the probability, amplify the probability of the marked element. Correct? What is happening? Each of these small things, take some small portion of it and amplify the probability of the marked element, right? And then we have to repeat it around n times to get success probability to be constant. What is the quantum algorithm? Exactly, right? We have learnt our lesson here. we don't want to add probabilities at each step. What we want to do is amplify amplitude. Okay, so the same picture I want to make, but I want to make the same picture with amplitudes. Okay, so if I make an equal superposition, what will be the amplitude of each of these n elements? 1 by root n, right? So now, if I start drawing it for amplitude, at the first stage, I will apply Hadamard. I will have equal superposition over every index. Every index will have an amplitude 1 by root n. Correct? What do I want to do? I want each of these to contribute some of the amplitude to the marked element. Not the probability, but some of the amplitude to the marked element. And it should become around 2 by root n. Around 3 by root n. In how many steps will it become constant? Around root n. If we can amplify amplitude, we can do this in, but can we amplify amplitude? So the idea is right there. How we will execute it is the question. Okay, makes sense? Right? I will just write down things in notation so that it is easier to see what it means to amplify amplitude. But this is what we want to do. This histogram which we have made for probability, which comes up from the dumb algorithm, we are saying quantumly somehow we want to make the same histogram, just replace probabilities with amplitudes. Okay, ready? Right? So clearly the main idea is coming from Elitzer-Widman, right? The first kind of experiment which we did long back, right? So now, initially I will be in a state 0, I apply Hadamard. Again I will assume that my number of elements in my list are 2 to the power k, so that I can write my index in k qubits. Okay, make my life simple. If your list is less than 2 to the power k, you just add some more extra elements. Doesn't matter, pick the closest power of 2 to that n. The order of root n will not change, right? Okay. So then, correct? Agreed? This will be my state. Right? But obviously, I want to use the oracle. Correct? So then, I will start with where I will get the function value, or whether it is marked or not. So xi encodes whether the ith element is marked or not. Correct? So I get this state. Right? Now, if only one element is marked in my list, what is the probability that I measure 1 in the second register? 1 by n. Right? So suppose my third element is marked, so this state would be and we very well know if right now I measure, I will get 1 with probability 1 by n. I can repeat this experiment multiple times. That will be exactly this algorithm. This is just the quantum circuit for this dumb classical algorithm. Create an Uckel superposition, apply the oracle, see if you have a marked element or not. You will get the marked element with probability 1 by n. You can repeat it n times, your success probability will become constant. Right? But we do not want to amplify probability. We want to amplify amplitude. That means I do not want to measure this state. If I measure, then I have already gone to the probability world. I want to amplify the amplitude given here somehow. Right? You see the problem? If I measure right here, then I'm back to my classical dumb algorithm. I don't want to do that. I don't want to measure here. I want to somehow now say that all of these give me some more amplitude, add up the amplitude here, right? So I want to amplify amplitude instead of probability. So how do I amplify amplitude? Have you seen an algorithm where you have amplified amplitudes? Yes, Elizabeth Budman, right? How did you do it? R theta by a rotation. So this is fine now, right? We have learned the lesson. So I can erase this lesson.